Yo, 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 YouTube, what is up? It's your boy, Mr. Robinson here in the virtual math classroom. It's so good to see you. Do me a favor, go and smash that like button right now and go and ring that bell if you want to see more math videos. That's right, I'm here to give you math videos, and I don't know why I'm doing this voice. This is one of the dumbest things I ever hear on YouTube. I'm not your boy, I'm your math teacher. You ready to learn some things on quadratic equations? I'm ready to do it. We're graphing. This is an integrated math 2 concept here. We're looking at quadratic equations and graphing them, looking at the vertex, looking at corresponding points, y-intercept, x-intercepts, different things like that. Couple word problems here and there. Vertex form, standard form, writing the equation of vertex form and converting into standard form, and so on and so forth. If you want to find the PDF of what I'm going to be doing right here, go down to the description section below and go ahead and download that PDF that you see at the very top, that first link there. And if you want to find a timestamp to a certain kind of problem that you see, go ahead and click that one. Once again, timestamps in the description section down below. I need to take a breath. I want to go ahead and get started on this thing, and I want to keep in mind and remind my students as well that there is a form of graphing that is almost completely tableless. Which is a shorthand notation of understanding quadratic behavior and using the stretch factor and the vertex to manipulate everything within. That's what I plan to do. I'm going to be doing a little bit of discovery with it as I talk on it. I've mentioned it before. I'd like you to keep practicing it. I want to keep encouraging it. Remember, you can always use a table. I will remind you what kinds of shortcuts you want to use a table to help you best, although I will not be using a table myself in the majority of these problems. Actually, probably not in any of them. However, when I'm graphing out of standard form, I do need to find the vertex by substituting in my x value in the vertex. You will be seeing me do that. After that, I will be referring to the stretch factor to find my remaining points. I hope you can follow along with how it is that I go about it. If not, go ahead and check it with the way that you do it using a table or what other methods you do have. So I'm just going to go ahead and get started right here, guys. I'm going to start with number 1, parts A through E. They are all graphs. The first 3 are in vertex. This is technically vertex or standard form, depending on how you look at it. And I'll actually kind of show you both concepts of this one, how it's both in vertex and standard form, and go with it that way. That way you see a little bit of vertex form, standard form, and what we do out of both of them. So I can do B and C out of vertex form, D and E out of standard form. Before I do actually begin, I want to throw out the idea of what vertex form looks like in general. Vertex form of a parabola is represented as such. F of x or y equals a times the quantity x minus h squared. That is a squared, plus k. I know that's going to bother you for the rest of this day here, so it's going to bother me as well. I'm going to change that once again. That is a squared. There we go, plus k. The vertex appears at h comma k. We use that opposite, same approach, opposite of minus h, so whatever's opposite of that is your h value. And then k is the same, opposite same right there. And then the stretch factor, the vertical stretch factor is at the letter A. Of course, that's going to be used in great detail. And put an equal sign there to not make it look too obtrusive. So that's the vertex form there. Standard form gives you some other bits of information that can help you a little bit. 3 bits of information, rather. Sort of. We got f of x, if you want to put it that way. F of x equals ax squared plus bx plus c. Now, the cool things about this is you can get your y-intercept. Your y-intercept occurs at the point 0, comma, c. All right. The vertical stretch factor is also a, just like the last one. That's why I use the same letter there. Vertical stretch factor is at a. And then the vertex can be found at the x value of negative b over 2a. That is the linear coefficient right here. And the quadratic coefficient, negative b over 2a. Comma, and then you substitute that x value into your equation to get the y value of negative b over 2a. To find the y coordinate of the vertex right there. Keep in mind, like I said, on parts D and E, and I'll even show you on part A here, that's what I'm going to do. Calculate negative b over 2a and then plug it into the equation. That's where you get the y value of the vertex. And then I graph using the vertical stretch factor there. I also have a third point I can find with 0, comma c. It's not a third point. That's a second point and a corresponding point across the axis of symmetry. I want to remember to keep talking about that as well. Let's do some problems, shall we? Part A. Y equals x squared minus 6. Now, anytime I'm going to do vertex form, I'll just go ahead and do it in purple to tie it in here. And standard form, I will do in blue. Okay? So I'm going to begin with vertex form here. If you want to get the appearance of vertex form for this problem, that is not purple. If you want to get the appearance for vertex form in this problem, you'd have to rewrite it as in, and I'm going to even show you what A is. A is 1. You aren't subtracting anything from x, so that's like saying x minus 0, quantity squared, and that's minus 6. The reason why this has both vertex form and standard form appearance here is because there is nothing in the parentheses around that x, which means that, we're subtracting nothing from there. So when we're looking at this in vertex form, you can see that the vertex of this guy is going to be at the opposite of 0 is 0. Of negative 0 is positive 0. It's just 0. And then same as negative 6. 0, negative 6 is the vertex. And, of course, the vertical stretch factor of A equals 1. All right. So when it comes to me graphing this right here, I'm going to start at 0, negative 6. Boom, like that. This is probably the more conventional way of wanting to graph it. That is not 6. 0, negative 6, one more down. Boom. And then I use my vertical stretch factor of 1 to observe this just like any old general quadratic equation, where if you go over 1 from the vertex, you go up 1 squared. If you go over 2, you go up 2 squared, which is 4. If you go over 3, you go up 3 squared, which is 9. Over 4, up 4 squared, which is 16. Remember, quadratics square. Now, vertical stretch factor of 1 means you multiply those heights by 1, which means those heights do not change. So over 1, up 1, because 1 is 1 squared. Over 2 from the vertex, up 4, because 4, once again, is 2 squared. Over 3, up 9, because 9 is 3 squared. And that's as many as I can fit, really. I don't think I can get up to 16. It would be somewhere kind of like there. That's over 4, up 16, which would be 4 squared. Okay, and I can reflect points across the axis of symmetry here. Now, I'm not going to be drawing this axis of symmetry because it's right on the y-axis right there. It's a vertical line that crosses right through our vertex. So across the vertex here, there are corresponding points of equal height. 1 away from the axis of symmetry right here, another point there. 2 away from the axis of symmetry here, another point 2 away. 3 away, 3 away, and 4 away, 4 away. If I really couldn't want to fit that, I'm only asking my students to graph 5 points, so like 1, 2, 3, 4, 5, and I give you 9 here. Completely without use of a table. Keep in mind, using a table on this one's not too bad. You square the numbers that I talked about and subtract 6. All right, not too bad for that, but you know what? If you do something consistently here, it's also not too bad. It's actually probably even better because you keep consistent and you keep fast and accurate. There's the graph in vertex form. Really, vertex form is probably the proper approach to do it here. To tie it in, though, and look at standard form, if I want to apply standard form ax squared plus bx plus c, and the same kind of thing here, I have my quadratic term and I have my constant term, and I'm missing my linear term. To equate this, this is like saying y equals ax squared plus the missing bx plus c. This missing bx means that b is 0. It means that b is 0 when we do this here, right? So there's the standard form fully filled out. Not that you ever have to do this, but this does help if you're trying to find stuff. For example, the y-intercept, if it's at 0, c, y-intercept at 0, c means your y-intercept here, whoops, is at 0, negative 6, because your c value is negative 6. There's the y-intercept where it crosses the y-axis. Hey, that's also the vertex. Now, let's say we didn't know that yet, right? Because you didn't have this purple graph yet. Well, the vertex appears at the following points. The x value is at negative b over 2a. Negative 0 is just 0, and 2 times 1 is 2. 0 over 2 is 0. So the x value of the vertex is at 0, whereas the y value at the vertex, you plug it into the original equation right here, and the y value of the vertex, you plug in 0. 0 squared minus 6 is 0 minus 6, which is negative 6. So the vertex is at 0, negative 6. I mean, that doesn't help me very much to say that the y-intercept and vertex are at the same point, when I already could have done all that just from straight vertex form right here. But I'm just, just bear with me on that. And the vertical stretch factor, once again, is 1, where I would still apply the 1, 1, 2, 4, 3, 9, 4, 16 concept, as they just multiply by a 1 and they don't change. And that is the final graph there, whether it's purple or blue, same kind of deal. The next two graphs, B and C, I will be doing straight out of vertex form in purple, straight up. They are already in vertex form. I might as well take advantage of that while they're there. So let's move on. Part B, f of x equals negative 2 times the quantity x minus 4 squared plus 7. The vertex of this guy is at opposite same. Opposite of negative 4 is positive 4. And same as 7 is 7. Vertex is at 4, 7. That's where I'll begin. These graphs don't have numbers. I do apologize. I know that this is an 8 by 8 grid, though. 8 across, 8 up and down. So I know that 7 is 1 away from 8. That kind of helps. And 4 is halfway between this. Hopefully you can tell that that's a thicker axis line. I can really see it on my screen. I hope you can as well. Anyway, that's the vertex. And the vertical stretch factor here, I'll just put A, is negative 2. The negative portion meaning this thing's going to flip over, and thank goodness, because if this is our vertex, I don't want to go upward here. I can't fit anything. I hope it goes downward, which it will. Let's get exact points and plot them without a table. Imagine me going down. Instead of going 1, 1, 2, 4, 3, 9, 4, 16, I got to double my heights. My going down. How much am I going to go down? Twice as much as 1, 4, 9, 16, etc. So 1, 1, nope. 1, 2. Let's double that 1 right there. 2, 4, nope. 2, 8. Remember, we started at 7, so 8 less than 7 is negative 1. 3, 9, if that's 8. 3, 9, nope. 3, 18. Way too low. I'm not going to fit that one. This one's really only going to fit 5 points in total. Where are the other 2 points? Well, that's a good question. The vertex also holds the axis of symmetry. Let me use a color I won't use in any other form here. The axis of symmetry is this vertical line that cuts right through the vertex right there, which says all my points reflect across this right here. With corresponding heights, such as this is 1 away, so there's going to be another point that's 1 away, and this is 2 away and 2 away. There's nothing wrong with counting 1, 2, 2, 8 over here. It's just maybe it takes a little more counting. That might be a little faster. I'll be honest, I got to look at this again and see where they ask for axis of symmetry. I believe they do later. Just to talk about it here, the axis of symmetry, the equation is at x equals 4. It's equivalent to the vertex x value. It's the vertical line that goes through there. I'm not going to say that each time. I just wanted to call attention. I do believe we hit that one later and talk about it. So here's the parabola that goes through there. Nice smooth curve. Nice smooth happy curve. A little purple waterfall that goes down right there. There it is. Nice. Trying to Bob Ross you guys here. He's the first ASMR inventor without knowing what ASMR actually meant or was. I don't know if he intended to do that or if that's just how he spoke to people. Like he talked to his parents. Hi, how you doing Thanksgiving here? I'm Bob Ross. Are you, you must be Mr. and Mrs. Ross, huh? Like, where are your parents? All right, part C, y equals negative 1/2 times x plus 3 quantity squared plus 2. Let's go to war. The vertex is at opposite same, negative 3 comma positive 2. I'm going to go ahead and fit that guy right there. Negative 3, positive 2, that's where I'm going to begin. Stretch factor of negative 1/2. Once again, the negative represents that we will be going upside down, frowny face instead of smiley face. And the 1/2, as opposed to 2, 2 meant we were doubling our heights downward from 1, 4, and 9. 1 squared, 2 squared, 3 squared. 1/2 means we're going to halve those heights. Halve, like divide them by 2. So going over 1 instead of going down 1, we'll go down half of 1. Boop, 1/2 right there. Pretty good. If you're my students and you're using Edgelastic, which is a computer tool-based thing for doing tests and such, unfortunately, we can't hit half points, so I would keep moving on if possible. Over 2 down 4, right? Nope, got to take half of that. Over 2 down 2. Half of 4 is 2. Over 3 down 9, nope, we got to go half of 9. Well, some people don't know that half of 9 is 4.5. I will mark it very lightly, but for the most part, you might be thinking not a fraction anyway, or that's a fraction. Let's skip the fraction ones. Let's go again. 4 squared is 16. Half of 16 is 8. So 1, 2, 3, 4, 5, 6, 7, 8 down. There's a nice little point right there. And reflecting points across, once again, they're not asking us to draw the axis of symmetry, so I'm not going to do it each time, but there's another point right there. 1 away. This is 2 away, 2 away. 1, 2, 3. 1, 2, 3. Just a small little point. And 1, 2, 3, 4. 1, 2, 3, 4. Sometimes it really helps to draw that axis to show exactly where it is. Make sure that you hit the right spot there. I always like the fraction ones because it gets a nice gradual, a nice gradual curve downward and gives you that nice example of beautiful looking waterfall like parabola there, especially those upside down ones. I like to describe them as waterfalls. I don't know why. It's not really waterfall-esque. It's really hard to draw on a computer screen, if you know what I mean. Good enough. I'm going to take that one. Hopefully you can take it as well. Anyway, hey, if you are a table user, you can plot points in a table. You just got to know how you got to construct your table. Now, I'm not going to do a full table thing with you, but what I want to keep in mind with you is you want to find your vertex first. You want to find your vertex first because you want to build your table around your vertex. So if I'm on part C right here and I know that my vertex is at negative 3 for x, that means when I build my table, I want to make sure that I know that negative 3 is right in the middle of that guy right there. Let's go a little better right there. Negative 3 is right in the middle because I want symmetry in my graph. And I want to make sure I can fit my points in my window. They wouldn't give you a graph that's completely out of the window with the vertex, just like I talked about right here. They wouldn't make a graph that goes upward. That's ridiculous. Or a vertex that's way over here off the graph. That's ridiculous. So we want to get points within our graph here, like negative 2 and negative 1, and negative 4 and negative 5. Now, one of the drawbacks with the table, among the fact that you have to plug points in and calculate everything under the sun and maybe get a common denominator and things like that, is you might not even recognize what will and won't be a fraction until you're very deep into it. For me, I'm saying when I go over 1, I'm going down half of 1. Oh, a fraction. I'll move on. I'm going over 2. Let's go down half of 2. That works. 3, half of 3. No. So I can work really fast with that. And again, that's one of the benefits you have. So that's the first thing when you're building a table there. Plug in negative 2. It's a fraction problem. Plug in negative 1. I guess you get the point 0. The other idea to this, and you should already know what this one is because it's part of your vertex. The other idea with this is whatever point, once again, only plot 2 points on one side so you can then just reflect them. You don't even really need these points in the table, except maybe to write that at negative 5, it's also 0 because the reflection, right? The reflection. This one's at, if you really want to know, it's like 1.5. So this is also at 1.5, things like that. There's symmetry. Again, I'm not a table user in that sense. You can do it. I'm discouraging it. I'm not requiring, but I'm discouraging it. There are other quadratic behaviors you can see and observe and practice, and I really hope you do. But alas, those are some vertex form graphs. I think we run into a couple later when we solve by graphing. I'm going to go ahead and move on, and let's look at standard form in blue down here for parts D and E. Here we go. These are in standard form. The vertex is not prevalent right here until or unless you go ahead and do that vertex thing. Before I do, I want to call attention to where the y-intercept is on this graph. And remember, the y-intercept is not necessarily the vertex, even though it was on part A. The y-intercept is at 0, negative 5. When x is 0, this term goes away, this term goes away, y is negative 5. That is a point that is on our graph. What did I just do? Oh, I hate when the undo undoes a lot of things that I don't want it to undo. 0, negative 5. That is a point on our graph, and I'm going to use that as something as a point of reference to make sense of the fact that you have even less table work, or over 1, up 1, and down 1, things like that. Okay, that's one point that's on our graph. The vertex value is achieved by the x value being at negative b over 2a. Remember that, it's at negative b over 2a. The b value here is 4, so we're going to do negative 4 over 2 times negative 1. The a value here is a negative 1. I can't see the 1, but it's there, I promise you. So that's going to be negative 4 over negative 2. Negative divided by negative is a positive. 4 divided by 2 is 2. So the x value of the vertex is at 2. The y value is achieved by substituting 2 in for x. This is something that I need to do. This is a must do here. It's the only table portion that I'm going to do. Now you have to be careful with this negative in front of this thing because it's not a part of what's being squared. The x squared is getting negativized. What I mean by that is there's a negative outside of this 2 that's being squared. I'm not squaring a negative 2. I'm squaring a positive 2 and making it negative. Plus 4 times 2 minus 5. So that is negative 2 squared is 4. Plus 4 times 2 is 8, minus 5. Negative 4 plus 8 is 4. 4 minus 5 is negative 1. Yeah, I got to do that work for that one. Maybe I don't have to write every step, but I do have to substitute 2 into there. So there is a point on my graph for this vertex, guys, that is at 2, comma, negative 1. Let's go. 2, negative 1, that is indeed my opposite. Same kind of, well, I shouldn't say that, but if this was in vertex form, listen, if this was in vertex form, this would be the equation. Negative 1 stretch factor and x opposite minus 2 quantity squared minus 1. Yes, it's possible to write this in vertex form once you know your vertex. There's an actual way to convert from vertex form to standard form without this portion here. It's actually more complicated than this, and this isn't complicated. It's just seeing this formula and then plugging in your number. There's something called completing the square that I'm going to teach in the next unit. That's going to be a little more, it takes a little bit more to do. But alas, I have some points here, and I'm going to continue finding more points with this. Keep in mind, guys, this is the vertex. Now, your stretch factor is negative 1. With the negative 1 stretch factor, what that means, once again, is it'll be flipped over. I mean, essentially, it's a frowny face like that, right? It's a frowny face. And this is also, no less, your axis of symmetry. Let me draw that guy. This is your axis of symmetry right here. It's going through the vertex, right? That means that that y-intercept that we found actually does have a corresponding point on its other side, over 2 over 2. I already have 3 points, and I haven't used, well, I can't say I haven't used a table, but I haven't applied the stretch factor yet. I haven't had to. It's not that I had to do the y-intercept, but it's just going to show you. Check this out. Stretch factor is -1. That means it is a 1, 1, 2, 4. There it is. 3, 9, 4, 16, things like that. So 1, 1, boom. 2, 4, there it is. Like I said, the y-intercept got me that point. And I can reflect this point over. This is really all I can fit. Listen, I know I'm talking a mile a minute with this thing, but this is a unit review in this case. And in this case, I also did a, well, I don't know if I did a video, like a practice quiz video or what have you, but I did. This is something we've been covering a while in our class, and this is no longer the For Dummies version. What I mean by that is I am not going to break this down just to rudimentary levels. These are things as if you've heard it before, and I'm just reapplying it over and over. So I hope that it's a concept that rings familiar and true with you, so much that you could probably teach it to someone else. Maybe you don't know all the ins and outs and the whys, but you have felt comfortable enough that you can demonstrate it. At least, teach it back to me as if I've heard it before. All right, and that's the graph. I use this stuff to help myself out there. You might say, oh, I wanted to use a table. All right, you still had to find the vertex. You don't know how far away this vertex might be from here. You just plug in -2, -1, 0, 1, and 2. Guess what? Your -2, -1 points are nowhere on this graph that you can see, and you landed on the vertex without even knowing whether or not it was the vertex. So you can't just use a table right in the middle. You got to find the vertex first anyway. So let's do it again. Part E, f of x equals 3x squared minus 12x plus 5. I'm going to go back to the idea that the y-intercept one more time is graphable in that we can identify it and it actually fits in the window. 0, 5, it's up here. That is not necessarily your vertex. In fact, it's not your vertex. The vertex here, how do we find that? Same thing as last time. Your x is going to be at -b over 2a. Your b is -12. So we're going to do negative b, opposite of negative, over 2a. A is 3. Opposite of -12 is +12. 2 times 3 is 6. 12 divided by 6 is, hey, 2 again. We got a 2 siding, just like last time. Sounds good. All right, well, let's find out the y value now. The y value, f of 2, we're going to be getting 3 times 2 squared minus 12 times 2 plus 5, okay? 2 squared is 4. 3 times 4 there, minus 12 times 2 is 24 plus 5. So that's going to be, I should have just written that as 12, my bad. Minus 24 plus 5. Now, you might have noticed last time that I got -4 plus 8, which gave me +4 here, +4. It was the opposite of this -4 here. Was it coincidence? Well, check this out. 12 minus 24. Anyone happen to know what that guy is? It's actually -12. It is true that when you substitute the vertex into standard form and you combine your first two terms after, exponentiating and multiplying and stuff like that, that it just becomes the opposite of that first term. Always. Always for these quadratics. -12 plus 5, though, that is -7. -7, okay? That's the y value of the vertex. So our vertex is at 2, -7. Our vertex, once again, is at 2, -7. So we are over 2 and down. What did I say? This was a 8 by 8 by 8. It's really a 16 by 16, but I mean like 8 that way, 8 that way. So it's at 2, -7, way down there. And we have another point that's way up there. And if you understood what I talked about, the axis of symmetry here, if this is 2 away from the axis of symmetry, there will indeed be another point over here. We are just 1 point and its reflection away from completing this. I will confirm that this is the right spot, though. Your stretch factor, your vertical stretch factor here is +3. That means instead of our parent function showing our from the vertex 1, 1, 2, 4, 3, 9, 4, 16, etc., we will be tripling our heights. Instead of 1, 1, well, 3 times 1 is 3, so we'll go 1, 3, boom. Let me reflect right now, across, there's that other point, 1, 3. Instead of 2, 4, you got to do 4 times 3, that's 12. We'll be going to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Hey, look at that. It's at 12 right there. Confirmed by the y-intercept that we already found. It's nice how all these things have very connective tissue. Very cool. Not a very good graph, though. Let's see here. Let's see if I can do this one for you. It doesn't have to be super pretty, but try not V-shape it. Everything is... This is not straight, by the way. This is a progressive curve that is sharpening this way over time more and more and more. There's never one part of this that is actually truly straight. Even if something approximates to linearity, it's never truly straight. It's always progressively sharpening at each instance of x, even the decimal parts. All right? Ugly, my bad, but gets the job done. So there's some graphing out of vertex and standard form there. There are the equations one more time, and there's a lot of information that was had just on number 1. This is good practice for an exam. I kid you not. All right, number 2, we have a word problem here. A ball is thrown from a building. The function h of t equals negative 4t squared plus 8t plus 50. They give you the model, that's good. Models the height h measured in feet of the building over time, t measured in seconds. Okay? The height of the building over time. What are they building? Oh, it's not a ball, it's a balloon. Look at this. Balloon, ball. This isn't my practice test, as you can tell. A balloon is thrown from a building. Well, it sounds weird. This should say of the balloon over time. So, my bad, guys. This is me not even looking at a practice test before a practice test is actually provided. Balloon, balloon, balloon. I was saying, why is a building progressively building? This isn't Tenet, where it's just forming itself from destruction here over time. Go see that movie, by the way. A balloon is thrown from a building, like, it's probably lost some helium, so it's like, all right, this function, the height, models the height of the balloon over time, and when it's thrown from a building, you assume you're on a rooftop, it's going to be one of those things, I'm not going to graph this, but if you did, you'd probably notice that it's one of those graphs that does something like this, like the vertex is probably like right here, and it's doing like that. We are going to perceive some part of this graph. I'm drawing dotted lines because if this is time, this is the part that matters. This is like, this didn't happen. Throw the balloon, it hits something and it goes wee and splat on the ground, I guess. Excuse me. We haven't seen many of these as a class, but the model can help us, we can answer some things here, and I'm giving you the visual representation of the answers that we get. In fact, they're going to ask us some questions here, like what is the balloon's maximum height? How long does it take to reach the height? How long is the balloon in the air? Things like that. Okay, so, you ready? I'm ready. Here we go. What is the balloon's maximum height? Now, a maximum or a minimum of a parabola occurs at its vertex. Okay? It occurs at its vertex, and because this thing is a negative a value, that means it will be an upside down parabola like I showed here. That's what all these gravity models will be talking about here. So we are trying to find this vertex point. Not that you know visually what this necessarily looks like unless you graph it. They're not asking us to graph it. This is just giving you the idea. But the vertex is the maximum height. It asks what is its maximum height. And it asks how long does it take for the balloon to reach maximum height, which is an interesting way that they're asking these questions. I would have preferred to answer part B before part A. Listen. I'm going to be answering the question here for what is maximum height. They're asking for the y value, or in other words, I should say, the k value of your vertex. If your vertex is at hk, in part A, they are asking for what is k. In part B, they are asking for how long does it take, that's time. Time is here. They're asking for what is h. They're asking for what is h, right? Here's h of t, here's the height, and here's t. So, oh, sorry, now there's another h in the way. That's confusing to hear. Let me get those out of the way. They're asking for the hk parts of the balloon. I'm going to get the h part first of the vertex because that's achieved from that negative b over 2a thing, right? So, can I answer B first for you guys? Is that okay? How long does it take for the balloon to reach maximum height? Because when we get that answer, we're going to be able to get this answer part A. So here we go. So for your vertex, the x value of your vertex, or h, if you put it, is at negative b over 2a. Negative b over 2a, okay? Negative 8 is here. 2 times negative 4 is negative 8, and that is a positive 1. So what this is telling you, when x is 1, or when t is 1, rather, I really should be using their variables. When t is 1, what it's telling you is, what did it say, in seconds? T is in seconds. It takes 1 second. It takes 1 second for the balloon to reach its maximum height. Got a wimpy thrower. Yeah. It's a balloon. It takes 1 second. for the balloon. This is a word problem. You got to answer in words, right? I should have typed it out. To reach its maximum height. Okay? There it is. 1 second. What is the balloon's maximum height? Well, now we get to substitute 1 in for t, excuse me. We get substitute 1 in for t, and then we'll figure out the height from that. And that will be the tallest height. That's at the vertex there. So h of 1, I'm going to use a different color after this. I'm getting blue blind. H of 1 equals -4 times 1 quantity squared plus 8 times 1 plus 50. All right. So that's going to be 1 squared is 1. -4 times 1 is -4. 8 times 1 is 8. And then a plus 50 here. Remember what I said before? -4 plus 8 is the opposite of that guy. It's 4. 4 plus 50 equals 54. So the maximum height, the balloon's maximum height, what do they say? Feet, measured in feet. The balloon's, I don't know why there's an L there instead of an S. The balloon's max height is 54 feet. There we go. See, I kind of needed B to answer A. Kind of weird it was asked like that. Okay, how long is the balloon in the air? Now, this is where the visual understanding helps, because what they're really asking us is, how long does it take to kerplunk? Right here. If h is height of the building, and we assume a building is built from the ground, we're asking when will it hit the ground? Okay, it starts up here, it hits down here, ground, something we need to solve for there, right? Honestly, not a question that we can solve this algebraically, but you know, now that I'm looking at this problem, you can't, darn it. We might have to graph this. If we were in, you know, I was thinking about this before, and I was like, no, we can solve it algebraically. You guys, we haven't solved algebraically yet. We have to solve this thing graphically, which means you'd have to graph and come up with the time when your height becomes 0. But what we are doing, we are figuring out when h of t here is 0. We're talking about that. I really wish they let us graph it now. This is gonna be kind of tough for me to talk about, because we don't have a big graph that's 54 units tall. I want to see if you can do this thing with me right here, okay? If you're asked a question like this on a test, it'd be something that you'd be able to already graph. I wasn't thinking clearly about this bit right here. So we need to find out what t value gives us 0 here. So when does -4t squared plus 8t plus 50 equal 0? Okay, that's what's being asked. Okay, so in terms of graphing this, without me actually graphing it, I want you to think in table terms. Here's x, here's y. I mean in table terms with my stretch factor concept. Here's vertex right here, 154, okay? I want you to think in my terms of vertex and stretch factor. This is a -4 stretch factor. That means instead of going over 1 up 1, over 2 up 4, over 3 up 9, over 4 up 16, over 5 up 25, etc. I'm sorry. As I'm looking more at this problem, guys, I'm sitting here going, this isn't conceivable for you guys to do. All right. Skip this part because it's not even an integer answer. Not an integer answer. If you're asked to solve right by graphing and you're doing something with this with graphing, that means it's graphable from your end and you can get an integer answer. Here we cannot. I'm sorry about this. I am. Let's not answer C. Let's go ahead and skip it. It's a very good question, and if we learned how to solve algebraically first, I would have loved to do it. We didn't. That's not the order that the book is teaching it. All right, I'm sorry. That just demoralized me. That was kind of weird. How tall was the building the balloon was thrown from? I guess their idea of saying it is where did, you're throwing it from the building's height, basically. They're asking for the y-intercept. They're asking what is the y-intercept of this guy here. That's what they're going to be asking on things like this. Hey, when did, like that. So the y-intercept is at 0, 50, right? 0, at times 0, the height is 50. So that means, how tall is the building? It was 50 feet tall. That's just a concept of throwing it. And remember, the balloon's not necessarily going outward. This is time going forward. You might have thrown it straight up in the air and the wind kind of just pushed it and then it went straight down. The point is, this is height at time 0 when you threw it, and you're on the building when you threw it, and that's just the idea. So 50 feet tall. 50 feet tall. I'm sorry about C, guys. I know the answer, or I don't know it. I know how to get the answer. It's not something that was taught. It's not something that was taught. It's not something that can be covered with this graph here. Okay, I'm going to move on. Number 3, solve each equation, graphically show all work. Well, my work I'm going to show is my graph. I'm not going to be using a table with these things right here, and I don't know if I apologize for that or not. But the idea here, this goes back to what we did with graphing absolute value functions. Let's say that this left side here in blue is an f of x equation, and let's say that the side in here is a g of x equation. And we're going to be graphing these as if this is f of x, or y equals 2x squared minus 8. And we're going to be graphing this one as if it is g of x here equals 0. Now, I'll have you know that it is much more preferred, not necessarily true, that it is, I'm going to take back what I said. It's not always much more preferred. It is sometimes preferred to just set it equal to 0 anyway. Then you're just asking, where does it cross the x-axis? It depends on your graph stuff. If your graph's really weird, maybe, maybe not. I'll show you both situations on part B, where I have it set equal to 8, and where I subtract the 8 over and set it equal to 0, and how you get the equivalent kind of graph. All right, anyway, but for part A right here, g of x equals 0, I'm going to go and graph that one first. That's y equals 0. That is a horizontal line. That is on the x-axis. It is this line right here. It is this line right here. The blue one is the one that we need to pay a little more attention to. This is also, if I were doing vertex form, this is 2 times x minus 0, quantity squared minus 8. That means your vertex is at 0. Your vertex is at 0, negative 8, like so. So I'm going to start it way down here like that, okay? Stretch factor is 2. Stretch factor is 2. 1, 1, 2, 4. Double those. Double those. 1, 2, 2, 8. Hey, it goes right back up there. Boom. 3, 18. This is 16 right here. 17, 18 is way up there. Reflect them over. Reflect them over if you could, if you want to. Boop, reflect it over. Now the graph goes through here. They say solve by graphing. I already kind of did where they cross here, but they say draw the actual graph, guy. All right, I'll draw it. And here's our graph that goes through these guys. Completely tableless. Oh, no table. Terrible looking graph, though. What they're asking, though, is what x values do these points intersect at? X values, not coordinate pairs. What x values? The x values are negative 2 and positive 2. That's your solution. That's it. All right, part B. Same kind of thing. If I treat it straight up right now as f of x in blue and g of x in green, we will be looking at f of x equals 1/2 times the quantity x minus 3 squared here. And then g of x equals 8. That means we are looking at a green line all the way up here, right? Y equals 8 is on that top line right there. And this one here, this blue curve, this quadratic, in vertex form, that's plus 0. That means the vertex is at opposite same, 3, 0. So I start at 3, 0 right here. And with the stretch factor of 1/2, I'll go over 1 up half of 1, over 2 up half of 4, over 3 up half of 9, over 4 up half of 16. Just like that. There's 1 point. Reflect the other ones across. 1 away, 1 away. 2 away, 2 away. 3 away, 3 away. 4 away, 4 away. Like that. You see where those things cross? Where they cross is my answer to this thing right here. And what are those x values? That is what's being asked right here. So let's check it out. That's going to be, boop, boop. That's x equals negative 1 and that is x equals 7. And what they really are asking is, what x values can I plug into this equation to make the left side equal the right side? Try and plug in -1 and 7 into there and see if you get the right side to equal 8, or the left side to equal 8, just like the right side does. Now, there's another way we could have done this problem, and that is if I subtracted 8 from both sides from the jump, I would have an equation that says 1/2 times x minus 3 quantity squared minus 8 equals 0. My f of x would be in blue right here. My g of x would be in green. I'm not going to completely regraph it. What I want you to know is, instead of the vertex being at 3, 0, it would be at 3, -8. And instead of this being at y equals 8, it would be at y equals 0. Basically, everything goes 8 down. The graph would instead just look like this right here. That's where I'd graph it. So you could set it equal to 0, find out where it crosses the x-axis. Boom, that's great. And you got those things right there. And that's the exact same answer. It still crosses at -1, 7 when you graph those. So it just depends on how you do it. I'll leave it as the original, just so it's the one we did together. All right, in part C, this one is in standard form, -x squared minus 4x minus 3 equals 0. There's something I want to do with this equation. I don't know if you'll make a lot of sense of it, but the fact that it is an equation means that you're allowed to do it. If I multiplied everything by -1 and by -1 right here, because whatever you do to the left side, you can do the right side, I have all positives here. You know what I mean? Why deal with a bunch of negatives when you can deal with a bunch of positives? If you don't understand that, though, then I shouldn't continue that way. I'm just saying this is something you can consider doing if you really don't like the looks of that thing right there and work it out. So I'm going to deal with the negatives because I want to deal with the challenge that you guys might have to undergo when it comes to a test and not recognizing you can do that. So here's my f of x equation right here. Here's my g of x. I'm not going to rewrite them one more time. You know what I mean. F of x is this. G of x is this. And what's this? Well, this is the x-axis, just like this. One more time. Boom. All right, now I have this one, this f of x guy. Now I got to do some work on this. I got to find my vertex. The vertex in this f of x equation, the x value is achieved by doing -b over 2a. b is -4, a is -1. You can see why I didn't like the negatives. This is actually where I don't mind the negatives. It's the next part that I don't like the negatives as much. Opposite of -4 is +4. 2 times -1 is -2. 4 divided by -2 is -2. A lot of 2's going on here, but this one's negative. So f of -2, the y value, when I substitute -2 into here, will be, here's where the negatives become trouble, the opposite of -2 quantity squared minus 4 times -2 minus 3. Oh, Mr. Robinson, I really wish you multiplied these by -1. Maybe. Remember, we don't do the opposite of -2 first. We do -2 quantity squared first. So this guy becomes +4, and then apply the negative outside of it. You get a -4 just from that term alone. -4 times -2 is +8, so you got -4 plus 8. I've seen that before. Minus 3. -4 plus 8 is 4. 4 minus 3 is 1. So your vertex is going to be at -2, 1, like that. So let's plot that. -2, 1. Boom, right there. All right. A -1 stretch factor means we will be going down instead of up, and we will be going the conventional 1, 1, 2, 4, 3, 9 route. So I'll be going 1, 1, 2, 4. By the way, -3 was the y-intercept here, right? 0, -3. There it is. 1, 1, 2, 4, 3, 9. Remember, this goes 8 down. 9 down from 1 is 8 down right there. And reflect, and reflect, and reflect. Oh, how you wish you were doing tableless graphing if you're still using a table, guys. That is so 90s. I don't know, it's so 80s. Come on, you guys are with modern times, right? Be hip. I don't know if it's modern or not. It's just, it's fully realized these days that this is just the behavior. This is the nature. The error of the ways. I'll tell you what, my teacher didn't teach me tableless graphing. I just acquired it. I just went ahead and said, yeah, this is a thing. I'm going to do it. Sorry, you probably can't see some of those points down there. There we go. All right, where's it crossing? What x values? That's -3 and -1. X equals -3. X equals -1. Those are the values that get me 0 right there. Hang on 1 second. I'm pausing this thing as I'm getting an important phone call I've been waiting for. 1 second. Okay, I'm back. You didn't even notice I was gone. All right, here we go. Solve by graphing. There it is. Let's move on. Numbers 5 and 6 are the same kinds of things. We have these graphs, and we're going to answer questions. Here we have axis of symmetry, things like that. So the graph is already there. Write it in vertex form. What is the vertex, and what are the approximate zeros? Let's start with let's go in order. Vertex form right here. The vertex of this guy appears to be at -3 and 1, 2, 3, 4, 5. -3, 5. And what you got to do now is determine what the a value is for the stretch factor. Here, let's do this. The vertex is at -3, 5 right here. You got to figure out the a value, the stretch factor, to write this equation, right? If we are going to write this in vertex form, we need some sort of y equals a times x minus h quantity squared plus k, all right? Now, what we got to do is use the vertex values hk that we have right here and get another set of values here, such as these ones here, this xy pair. And this is at -1, -3. We got to substitute that the x and y right here, the h and k right here into this whole equation and solve for a. So I'm going to kind of be doing some work over here. Get ready. Y is -3. I got -3 equals a times x is -1 minus h. That's minus -3. That means plus 3, right? Opposite. Plus 3 quantity squared plus k. That's plus 5, right? So -3 equals a times -1 plus 3 is 2. So we got 2 squared there plus 5. I really should subtract that 5 over at some point here. I'm going to do -5 minus 5. And now I have, running out of room, -8 right here. And 2 squared is 4. So I got 4a. Divide both sides by 4, and I get a equals -2. So the equation in vertex form is y equals -2 times, and now I got to use the vertex points, opposite, same, x plus 3 quantity squared plus 5. Okay? That is the vertex form part right there. The approximate zeros are where it crosses the x-axis. So they're asking you approximately what x values are we crossing the x-axis at. So I'll say these zeros are approximately at about -1.5 and 1, 2, 3, -4.5. I'll let you know if you're my students taking a test, it's going to be crossing at integer values. It won't be at decimal values like this where you're approximating it. So I hope that's okay. Write the equation for the axis of symmetry. Okay, well, that is the vertical line that goes down the middle of the vertex right here. The equation will be an x equals equation because it's crossing at -3 for x. The equation of the axis of symmetry is, x equals -3. All right, write the function in standard form. So you have this function in green right here. We got to rewrite this in standard form by expanding the x plus 3 quantity squared portion, distributing the -2 into that portion, and then adding 5 to that result. So I have this y equals -2 times x plus 3 quantity squared plus 5. I'm going to go ahead and expand this squared portion. That's y equals -2 times, here we go. In expanding this, x plus 3 quantity squared, if you guys remember here, a plus b quantity squared equals a squared plus 2ab plus b squared, meaning we square the first term, we're going to square the x. We are going to double the product of a and b. We're going to double the product of 3 and x. Double 3x is 6x. And we are going to square the last term. The b is 3. 3 squared is 9. If you want to square conventionally, guys, just do x plus 3 times x plus 3 and FOIL it. I'm not going to do that. That's something you can do. Plus 5 right here. Okay. So when I distribute the -2 now into these guys here, I got y equals -2x squared minus 12x minus 18. Remember, it's a -2 on all three fronts there. And we got a plus 5 right there. -18 plus 5 is -13. So the final answer there is y equals -2x squared minus 12x minus 13. There it is. Negative 2x squared minus 12x minus 13. So the y-intercept is at 0, negative 13. It is out of reach of this graph. It is down there somewhere where my picture is that we can't see. But that's where it would be. Does this function have a max or min? What is that max or min? Since it is an upside down graph, it hits a top point that makes this a maximum. Okay, this guy right here is a max. And the max has to do with the y value. The y value is 5 at the vertex. So it has a max of 5. That's all we're going to say, max of 5. That's it. All right, I'm going to do another problem that's very much like this. This is another parabola. I think they ask the same kinds of questions. So let's try this again, shall we? Here we go. No, by the way, you might have noticed that we skipped to number 4. This is number 3. We skipped number 4 to do number 5. That was solving problems algebraically, something that we're going to be doing next unit. Probably why that number 2 question asked a question like this. It assumed you were doing some algebraic solving or assumed it was graphable. It was neither that was going to be good for what we're doing here. This is very algebraically done and something we're not doing till next unit. And again, I apologize for that. I didn't really preview. I didn't preview that problem. They had the word ball and building when they both should have said balloon. So keep that in mind too. All right, number 6. Use the function. Same questions as far as I can see. Same questions here. Different graph. Write the function vertex form. What is the vertex? What are the approximate zeros? So right here, I'm going to start with vertex just like I did last time. The vertex is at 3, 1, 2, 3, 4, 5. Is that 3, negative 5? I think that's opposite of what the other one was. Wasn't the other one negative 3, 5? I think so. So the vertex is at 3, negative 5 right there. Remember, that is your h and k. That is your h and k. Let's just do the zeros first. Let's get them out of the way. The approximate zeros is where they're approximately crossing the x-axis here. Very close to the origin at 0, 0. So this, as far as the zeros here, it's at x equals about 0 and about at x equals 1, 2, 3, 4, 5, 6. I'm just going to go ahead and say 6. If this is all about being 3 away, right, as far as reflection points go, then if this is 3 away, I'm going to call that 3 away. Say that's 6. Good enough for me. Like I said, yours will cross actually at integer values. To write the function in vertex form, once again, it's going to be with this equation here, y equals a times x minus h, quantity squared plus k. We got to figure out this a value and stretch factor. I already know it's going to be by looking at it, but here you have to choose an x, y value that is not the vertex, such as this one we have right here. This is at 1, 2, 3, 4, 5, and negative 3. Man, all these 5s and 3s showing up right here with opposite signs of each other, right? So if this is an x, y value that we know, and if this is an h, k value that we know, we're going to substitute them into this equation that we know to get an a that we want to know. So the y value is negative 3, so we got negative 3 equals, we got a times x, which is 5, minus h, which is 3, quantity squared plus k, which is minus 5. Look at all them 3s and 5s, huh? All them 3s and 5s. I'm just going to go ahead and add 5 over right now while I have it in memory. Plus 5. And meanwhile, on this next step, I'm going to do 5 minus 3 here. So we got here now, negative 3 plus 5 is 2. And we got a times 5 minus 3 is 2. And 2 is being squared. We go from 3s and 5s to just 2s now, huh? Here we go. 2 squared is 4. Uh-oh. So we got 4a equals 2. Divide both sides by 4. A equals 2 over 4. Be careful. A lot of people say 2 in that thing. A equals 2 over 4, and 2 over 4 reduces to 1/2 as a fraction. So our final equation there is y equals 1/2, which is what I predicted, times x minus 3 quantity squared minus 5. Remember, opposite and same right there, and that's the vertex form. So we answer all 3 questions on that blank bit there. I don't know why they weren't just different things. I did them way out of order, and they're in way weird spots, and all in different colors. I apologize for you when you're going to have to do this. Write an equation for the axis of symmetry. Oh, great. They give us a great big thing there. I totally forgot about that. Axis of symmetry is the great big line that goes right down here, the vertical line that cuts through the vertex. That is at x equals 3. Axis of symmetry, x equals 3. Thank you for giving me all that big space for that. Write the function in standard form. I kind of need that space right there. I got this guy right here, and I got to multiply by 1/2. Maybe it won't be very fun for some of y'all. Let's take a look at what we're going to do with the fraction here, okay? So we have, let's use blue. I haven't used too much blue here. I got y equals this equation here. I'm going to just go ahead and, okay, keep this equation in mind. I'm going to expand x minus 3 quantity squared, which means I got to do the equivalent of what we would do if we had a minus b quantity squared. Which is a squared minus 2ab plus b squared. Remember, you can always do x minus 3 times x minus 3. I am not stopping you. I am not stopping you. So y equals 1/2 times, here's the expansion. We square the first term, x. We double the product of x and negative 3. That'll be negative 6. Oh, sorry, x squared. We double the product of x and negative 3, with negative 3x doubled, is negative 6x. And negative 3 quantity squared is 9. The 9 is going to be added to that right there. Minus 5. Okay, we got to take half of these things right here. Here we go. Distribute the 1/2 into x, negative 6x, and 9. We're going to get y equals 1/2 x squared. 1/2 of negative 6 is negative 3, so minus 3x. And here's everyone's least favorite part. Half of 9 is 9 over 2. Yes, I'm going to leave this as an improper fraction. Minus 5 right there. 9/2 minus 5. How do we do that? Let's get some side work. 9/2 minus 5 over 1. Get a common denominator of 2 right there. That's going to give us 9/2 minus 10/2, which is negative 1/2. So your final equation for this guy here is going to be y equals 1/2 x squared minus 3x minus 1/2, as we got those combined right there. And there it is. Oh, how you're so wishing we just had vertex form all the time. Well, sometimes you'll have fractions on these guys as well. I can promise you that. Kind of makes sense that it crosses that negative 1/2 for the y-intercept. There it is. You see that right there? That's nice. You got it. Anyway, so that is the standard form of that. Not very pretty, but it's something we can work toward. Does this function have a max or min? What is the max or min? It is a minimum because it's crossing down here at the, or not crossing, it is a vertex at the bottom. That is absolutely a min, and it is at the y value of negative 5. It has a min of negative 5. Okay, there you go. There you go. Minimum negative 5. All right, moving on forward. Number 7, here we go. Use each table to write a quadratic form in vertex and general forms. Another phrase for general form is standard form. Standard forms. That's what I've been using. Show all work. I thought it said good luck for a second. Good luck. All right, guys, I'm going to make this plain and simple. I'm going to choose one set of x, y values from, it's basically the same thing as we did last time in the last two problems that we did. You have the vertex identified at 1, negative 7 right there. These are other points that exist on this graph, which they did not draw, but it's, something that does that. And we got to choose another set of points to identify as our x, y. So if this is our hk, we need an x, y. I'm going to choose just something that's nice and small and close, so like this one, x, y. Any xy that you choose on here will give you the same a value no matter what you do if you do the math right. Now remember the equation we're referring to. It is, they have an f of x here. So it is y equals, or f of x equals, a, you know what, I'm going to use y because we're substituting y, right? Y equals a times x minus h quantity squared plus k. So here we go. We have our hk at 1, negative 7 and our xy at 2, negative 3. Our y being negative 3. A we need to find out. X is 2 minus 1 minus h squared plus k is minus 7. All right, I hope you can do this with me. Add 7 to both sides. Negative 3 plus 7. Okay, that's 4. I want to save room and time. 2 minus 1 is 1. And 1 squared is 1. So 4 equals 1a, or 4 equals a. That is the a value. Good. We need that for our vertex form. So your vertex form here will be y equals 4 times x minus h minus 1 quantity squared plus k is minus 7 right there. There's the vertex form. I don't know if they wanted it right here on this line since we have to do vertex and standard forms here. Good luck is what I thought it said once again. Standard form is going to be y equals ax squared plus bx plus c. Not that I need to write that, but the general idea once again is we have to expand this x minus 1, distribute the 4, and then subtract the 7. So let's go to war. Let's go to work here. Expand the x minus 1 quantity squared. That is, you square the first term. You double the product of negative 1 and x. You square the last term. There you go. Minus 7. Distribute 4x squared. Distribute minus 8x. Distribute plus 4. All right. 4 minus 7 is negative 3. So that's me 4x squared minus 8x minus 3. There we go. There's standard form. Yeah, I'm not writing on that line. That line looks cursed. I'm good. I'm good. All right, part B. Here we go. After this one, there's one more word problem. That's it. I say that's it. We hit the hour mark. So, part B, vertex is at 1, 2. So here is my HK. Let's pick an XY. Why not just get one that's to the right? I kind of like putting one that's just to the right of it because we do X minus H, if you know what I'm saying. I got to do 2 minus 1. You know what I mean? But anyway, so there's an XY right there. Well, heck, here. Let's do a big one. I know you're not a fan, but let's do a big one. You can try another one and confirm you get the same answer. How's that sound? XY. See that we get the same A value. All right, here we go. Same equation right here. Solve for A. Y is 47. Lucky number 47. A times X, which is 4, minus 1 quantity squared plus K. That's plus 2. Subtract 2 from both sides. That's going to be a 45 over here. 45 equals A times 3 quantity squared. Well, 3 squared is 9. So 9A is 45. Divide both sides by 9. You get A equals 5. It's still not bad. That's like a big number. Kind of worse if you get some negatives there. But A is 5. So your vertex form is going to be y equals 5 times X minus 1 quantity squared plus 2. There you go. There's your vertex form. And guess what? This is another X minus 1. I wish they were more creative so we didn't just expand the same thing here. So if you want to make this very fast, guys, X minus 1 quantity squared, once again, is X squared minus 2X plus 1. So we get Y equals 5 times X squared minus 2X plus 1. And then there's a plus 2 on the outside. Distribute the 5x squared minus 10x. 5 times 1 is 5, so plus 5, and plus 2. So we got y equals 5x squared minus 10x. 5 plus 2 is 7, so plus 7. There's your thing there. One thing I can call attention to here that I didn't mention on these last two problems here, the y-intercept of negative 3 is shown right there where x equals 0. That's your y-intercept. And the y-intercept of 7 right here is right there when x equals 0. So there's another little confirmation that's kind of nice you get to work with. These all have connective tissue. That's what I kind of keep saying there. And the last problem, number 8 that we have, is a ball is dropped from a 70-foot building. So it's a lot of stuff like the last one here. I sure hope that they, I'm already seeing this right now. Guys, I'm skipping part C. I can't be answering it with this graph stuff. I'll show you the relevance of what it means, but I can't do it unless we do it algebraically, and we can't do it algebraically because we haven't learned it. All right, a ball is dropped from a 70-foot building. The function h of t equals negative 8t squared plus 70 models the height. H measured in feet of the building over time t measured in seconds. They said building again. It's really of the ball. This is really of the ball, the height of the ball, because the building's not changing height. There we go. Unless it's a balloon again. It's a balloon again. It's a balloon. This is just why do they have this problem? We just did one like this. All right. What is the balloon's maximum height? So this goes to vertex again. And how long does it take to fall? Oh, this is a different question. How long does it take for the balloon to fall? 20 feet. I'm at pause again because we can't. Okay, we can answer these two. We can answer these two because it's a different kind of problem. We just got to take square roots. We'll do this. They're not going to be integer answers. What is the balloon's maximum height? We got to find the vertex K value. The K value. Okay, to do that, we got to find the h value. You know what I mean? It's standard form, but it's also vertex form right here. This is one of those. This is -8 times t minus 0 quantity squared plus 70. You know, that's what this thing is. If I expand that in that vertex form appearance, that means your vertex is at 0, 70. At time 0, the ball is at its highest height. That means it says it's dropped. It's not thrown up and then gravity takes down. It's just dropped from top. So that's 0, 70. 70 is the maximum height. Balloon's max. Oh, sorry, it's a balloon, not a ball. Balloon's max height is 70 feet, just like the building. It's dropping right from the building. How long does it take for the balloon to fall 20 feet? Okay, what they're asking for you, right? If a balloon falls 20 feet from its 70-foot height, well, 70 minus 20 is 50. Now, there's another way to talk about this, but I'll get to it later. This is for h of t. H of t. This is the height. We need to find out when 50, what t value is when we make this equation here. 50 equals. So this is 50 equals -8t squared plus 70. All right. I can subtract 70 from both sides, and I get -20 equals -8t squared. This is where things get a little messy. I'm going to divide both sides by -8. And I get t squared equals -20 over -8 is, I'm trying to reduce this as a fraction, is positive 5 over 2. I'm going to take that back. Yeah, no, that's fine. It's 5 over 2, which is 2.5. And therefore, t is the square root of 2.5. I'm not going to answer that any more than that. I don't know the approximation. 2.5 seconds. This is the kind of thing where I said this isn't a fun one for me to kind of do with you. How long is the balloon in the air? That means how long does it take for the balloon to hit the ground? How long does it take for the height to be 0? So same kind of thing with the equation. 0 equals -8t squared plus 70. And I'm speaking about this as if I'm speaking to my students. I'm going to add at squared this time. I like positive numbers. I'm speaking to my students. If you're another student in another class and you're like, hey, I learned to solve algebraically. I want to learn how to do this stuff with you. Yeah, I'm talking to my students on this one more, so I do apologize for that. Take the square, let's see, simplify that thing. Divide by 2, I get 35 over 4. So, which is 8.75. So t here is the square root of 8.75. It's really close to 3, but 8.75 seconds there. I'm done with those two problems. My students aren't going to be doing those problems anyway. All right, guys, that's going to be it for this video here. I'm sorry that I didn't preview this stuff before. This is something that was given to me by another teacher within our department. I'm not putting them on blast either, but it's something where, you know, if we're prepping for a test and we got to make sure we're covering problems like that number 4, right? We crossed out that problem number 4 because we're not doing it on the test. But these kinds of problems would only be hit on the test as well if we could graph them. This whole thing is about solving graphically, not algebraically, and I do apologize for that one. All right, so this is Mr. Robinson, guys. Thank you for watching. Take care.